Hi, I'm Herb Gross, and welcome once again to our Math as a Second Language lecture series. And today we're going to be talking about the topic called the weighted average. It's often a topic that isn't discussed in the elementary school curriculum, but which I think is an important one, and I'll show you why as we go along. But there's a more important element. Have you ever heard, I've heard people in different disciplines say, I'm teaching history, there are different opinions, but in math, everything is so cut and dried. And what I want to do is to dispel that notion today. I want to show you that math is far from cut and dried. It's only cut and dried once you know what it is that you're supposed to be doing. And by the way, if you think this is peculiar to mathematics, it happens in English grammar. I don't know exactly, maybe it's not English grammar, but I remember in school, we learned something called adages. Do you remember those? And I now call them dueling adages. For example, we memorized look before you leap. Anybody remember that? Yeah, I think you do. That's a nice adage. Be careful, look before you leap. The second one says, he who hesitates is lost. These are both acceptable adages. Look at them together. They contradict each other. If you look before you leap, then you're hesitating. And this says if you hesitate, you're lost. Okay? And if you don't hesitate before you leap, if you don't hesitate and you're going to be lost, you're not looking before you leap. You cannot do both of these at the same time. So how can we state both of these? If one contradicts the other, how can they both be true? And the answer is, in any given situation, you have to decide which of the two is the right one to use there. And once you make that decision, and you have to make that decision, and that decision is not cut and dried, then the logic is cut and dried after that. There's pairs of dueling adages. How about absence makes the heart grow fonder, but out of sight, out of mind. By the way, I had a Southeast Asian student who had heard the phrase that out of milk means you have no milk left. If you're out of bread, you have no bread left. So she thought that out of sight meant that you were blind. And out of mind meant that you had no mind left, so you were crazy. I mean, these are the kind of things that can happen with misinterpretations that come from language. Well, all I want you to see is there are dozens of dueling adages pairs. Too many cooks spoil the broth, but two heads are better than one. The same thing is true in math. Some people say, look, you just taught us that 1/2 plus 1/3 is 5/6. I want to know why I can't add across. Why can't I say that 1/2 plus 1/3 is 1 plus 1 over 2 plus 3 is 2/5? And the answer is, of course you can say it. I just did. The real thing is, when do we use which one? So, for example, suppose you work for me 30 minutes one day and 20 minutes the next day. That's 50 minutes. You expect to get paid for 50 minutes, okay? Let's translate from minutes into hours. 30 minutes is a half hour. See, it takes what? 2 30-minute batches to make an hour. There are 3 20-minute groups in an hour. So 20 minutes is 1/3 of an hour. So adding 30 minutes and 20 minutes as a minutes problem becomes adding 1/2 plus 1/3 as an hours problem. We know that the answer has to be 50 minutes. There are 60 minutes in an hour, so it's 50 of what it takes 60 of. So the answer is 5/6 of an hour. If you added across, okay, and you said, well, 1/2 plus 1/3 is 2/5, notice that an hour is 60 minutes. 1/5 of an hour is 60 divided by 5 is 12. 12 times 2 is 24. So if you were to believe that 1/2 plus 1/3 is 2/5 in this situation, you would be willing to accept 24 minutes of pay for 50 minutes of work. In other words, our real-life experience tells us if you want the right answer to this problem, you have to add 1/2 plus 1/3 in a way that gives you 5/6 as an answer, okay? So there's a case where 1/2 plus 1/3 equals 5/6 is the correct answer, but 1/2 plus with the circle around it, 1/3 equals 2/5 is the incorrect answer, okay? Now I'm going to show you something that may amaze you a little bit, but once you see it, it won't be so surprising. I'm going to ask you you're going to think this is a trick question, because if it wasn't, why would I ask you such an easy question? Well, it is kind of a trick question. I use the word trick whenever the answer isn't obvious or where I expect the person to instinctively blurt out the wrong answer. You're going from town A to town B at a constant speed of 30 miles per hour. When you get to B, you turn around and make the return trip at 20 miles per hour. So you go one way at 30 miles per hour, the other way at 20 miles per hour, and the question is, what was your average speed for the round trip? Can you visualize most people saying, well, it's 30 one way, 20 the other way. The average of 20 and 30 is 25, so the average should be 25 miles per hour. Can you picture people thinking that way? Because that's the way most people think. They just blurt this out. Now, let's watch what really happens. Let's pick a distance just to see what's going on here, what I call a reality check. Let's pick a distance that's divisible by both 30 and 20. Let's assume then that the distance between A and B is 60 miles. That means the round trip, RT, round trip, is 120 miles, right? 60 one way, 60 the other way. At 30 miles an hour, it's going to take you 2 hours to go 60 miles. And at 20 miles an hour, it's going to take you 3 hours to go 60 miles. So altogether, you went 120 miles. How long did it take? 2 hours plus 3 hours. That's 5 hours. 120 miles per 5 hours. 5 goes into 120, 24 times. And the answer is not 25 miles per hour, but 24 miles per hour. And the cynic can say, my God, what happened to the missing mile per hour? Well, there is no missing mile per hour. And let me show you why. See, let's break this down. 30 miles per hour is 30 miles every 60 minutes. That's the same as 1 mile every 2 minutes. So in traveling at 30 miles an hour, to go 1 mile took you 2 minutes. 20 miles per hour is 20 miles per 60 minutes. That reduces to 1 mile per 3 minutes. See, 20 goes into 60 3 times. So going the other way, it takes you 3 minutes. So what did you do? You traveled the 1 mile in 2 minutes going one way, and you traveled the same mile coming back in 3 minutes. When you make the round trip, you go through every mile twice, once on the way up and once on the way back. So if you went 1 mile in 2 minutes this way and 1 mile in 3 minutes this way, for the round trip you did what? You went 2 miles in 5 minutes. How did you get this? 1 mile plus 1 mile is 2 miles. 2 minutes plus 3 minutes is 5 minutes. So I went 2 miles every 5 minutes. There's 60 minutes in an hour. There are 12 5-minute segments in an hour, you see? And 12 times 2 is 24. Now, why did this happen? It happened because you spent a longer time traveling at 20 miles an hour than you did at 30 miles an hour. That's why it's called the weighted average. You see, if you had spent the same amount of time at each speed, in other words, if I went 20 miles an hour for 5 hours and I went 30 miles per hour for 5 hours, then the average would have been 25 miles per hour. But since I'm traveling at the slower speed longer, okay, it means that the average is going to be closer to the slower speed than to the faster speed. And I can show you this in terms of a picture. It's not that hard to see, I don't think. You see, here's the 1 mile. I'm looking at that as the cornbread. And in one case, the cornbread is split into 2 pieces. That's why I call these B for big pieces. In the other case, going the mile the other way, the cornbread is split into 3 pieces because it takes you 3 minutes to do the mile. These are smaller pieces. If you take 1 big piece and 1 small piece, obviously that's less than taking the 2 big pieces, but more than taking 2 of the 3 smaller pieces. You see? So what's happening is here, there are times when the correct answer is found by finding the weighted average, and other times when it's found by adding the fractions the usual way. The amazing, I shouldn't say amazing, a very nice thing about the weighted average is it always has to be between the two fractions. It's always going to be between the two fractions, okay? In other words, it's going to be bigger than the smaller one, but smaller than the bigger one. In fact, let's just check that out for a second, just in that simple case of 1/2 and 1/3. We have 1/2, we have 1/3, and what did we say? You're going to add across 2/5, okay? If we pick a common denominator, which in this case would be what? 30? Let's pick 30. A half is the same as 15 out of 30. A third is the same as 10 out of every 30. And a fifth, 5 goes into 36 times. 6 times 2 is 12. So if we pick a combination, see, again, if you want to make these sound like real-world things, if you can buy 1 pen for $2, that means you'd get 15 pens for $30. 1 pen for $3 says you'd get 10 pens for $30. 2 pens for $5 says that for $30 you would get 12 pens. You see, 30 is 6 groups of 5, so every time you took 1 group of 5, you're getting 2, so you're getting 2 6 times. Notice that now that we have a common denominator, we can compare the numerators, and just as predicted, the 2/5 is bigger than the 1/3, but smaller than the 1/2, okay? Again, I just wanted to show you in this lesson that students are going to add the fractions incorrectly, and I think it's a negative experience to say, that's wrong. What you can say to them, and this is what I used to say to my students, my goodness, you've solved a much harder problem that I didn't even know you knew how to do. My goodness, you found the weighted average. See, in other words, make it a positive experience. It is natural to add across. And later we're going to multiply fractions, and remember, you multiply across. Why is it logical that you can multiply across, but you can't add across? The answer is yes, you can add across, but it answers a different problem. It's not the way you would add 30 minutes and 20 minutes. Now, with that in mind, to show you a nice way to use the weighted average, here's a nice practice problem for you to do. Remember what a practice problem is. You pause the video, look at the problem, work on it, get the answer, and then once you have the answer, you come back, start the tape up again, and watch my solution just to compare it with mine. Or if you weren't able to do the problem, watch my solution, okay? Now, mechanically, this is a pretty easy problem to do. Remember, we've established the fact that the weighted average is between the two fractions. So if I want to find the fractions that's between 181 275ths and 99 129ths. By the way, notice what a cumbersome job this would be to find a common denominator and compare them and then find out how to find something in between. If we just add across, look what happens. 181 plus 99 is 280. 275 plus 129 is 404. And that tells me very quickly that one fraction that's between these two given fractions is 280 over 404, which, by the way, they're both divisible by 4. So I can divide out a 4. See, 280 divided by 4 is 70. 404 divided by 4 is 101. And so 70 over 101 is going to be bigger than one of these fractions and smaller than the other. I think it's kind of torturous to say to a person, find the common denominator and compare the size of these 3 fractions. If you don't mind kids playing with the calculator, there's nothing wrong with a calculator as long as you don't use it as a substitute for logical thinking. If they did this on the calculator, if they divided 181 by 275, they would get 0.658, and I'm rounding off because it's a long decimal. 70 over 101 turns out to be 0.693. By the way, later when we do decimals, I'm jumping ahead here because as teachers, I can assume that you've seen things that the students haven't seen if you're teaching sequentially, so I figure it's all right to jump to decimals this way. I always put a 0 in front of the decimal point because otherwise if somebody just saw this, they might not be sure whether that was a decimal point or just a mark on the paper. So I like to put a 0 here, and that should remind people that this dot is there for a purpose. But look what happens. 181 over 275 is 0.658, 658 thousandths. 99 over 129 is 767 thousandths. I use these squiggly marks to mean approximately equal because I've rounded off. And what is 70 over 101? It's 0.693, which is bigger than this one, but smaller than this one. And by the way, notice that the value, is, if we look at this in terms of decimals, is closer in value to this one than to this one. And the reason is weighting factors. This fraction contributed 275 parts. This fraction only contributed 129 parts, so the weighted average should be slanted towards this one, which it actually is. And again, it's not so much the weighted average that I want you to get out of this. I do want you to see that there is a positive result when the students do, and they will do it, add across instead of finding a common denominator. I think it's very nice to be able to show them this. But more importantly, I'm hoping that one of the things that you take away from this lesson is that there is a creative side to mathematics that is the same as the creative side of any poet. In other words, you look at a given situation and your mind has to figure out what the recipe is. If you want to see this in terms of a calculator, the calculator will not tell you what recipe to use. You have to be equipped enough in terms of your knowledge to tell the calculator what to do. Once you tell the calculator what to do, the calculator will do it quicker and possibly more accurately, more effectively than you would have done it by longhand. There's a partnership. One does the thinking, the other does the manual labor, okay? Well, again, I think that's enough for today. I enjoyed presenting this to you. It's one of my favorite topics. And I look forward to seeing you all again next time. And until next time, be well, stay young.